Hello everyone and welcome to the next part of the previous lecture. So in this part we are going to talk about the role of complexity, the characteristics and levels of software design. So extending the previous concepts, in this part we are going to understand what is complexity and how we can attack or basically manage the complexity. So let's get started. Now, before we start discussing about complexity, we need to decide that what type of difficulty this complexity is imposing. So generally speaking, complexity is considered to be an essential difficulty which is part of the software. Now we will definitely discuss later what is an essential difficulty, and we will also come to know that there is another type of difficulty which is called accidental difficulty. But before that, we can read this out as software has the following properties in its essence. One of them is complexity, conformity, changeability and invisibility. So by complexity, we are going to understand what does complexity means and what difficulty does it impose in the software. But conformity is one of another property which the software should have, which is that it should conform to the requirements which are given by the user. It should conform to the design which is actually created. So all of these aspects follow under the category of conformity. And then another property, essential property of software is changeability, where the software needs to evolve. It cannot remain the same. It needs to change over time. It needs to evolve with the requirements of the user, or with time, with the competitors in the market. And the last essential property of the software is invisibility, where if we talk about the development process, the invisibility is that I really cannot foresee when this software is going to complete. I cannot foresee what will be the actual budget at the end of the day. So there is an inherent invisibility in the development process of the software. And when again we talked about the physical properties of the software, we say that fine, software is an intangible in nature. So by that we mean that we cannot touch software. So that's again an essential property, and the product that we cannot touch, we cannot feel, would definitely have different dynamics and different aspects to be taken care of. Now, generally speaking, we have divided the difficulties related to software development into two different classes, which are of course categorized by one of the author called Brooks. One of the category is essential and second one is called the accidental difficulty. So these are two different types of difficulty. So if we look for the philosophy, it says that the essential properties are the properties that a thing must have in order to be that thing. So for example, car must have an engine, it should have wheels, it should have doors. So basically without these components, that particular thing cannot be that thing. By this I mean that car cannot be a car without an engine. And whereas the accidental properties are the properties that a thing just happens to have. For example, a V8 or a turbocharged 4-cylinder engine, 2 doors or 4 doors. So again, that's an additional element, or that's just an accidental property where some cars does have that property and the others actually does not have. Now, if we discuss the same concept in terms of software, so we would say that essential characteristics or essential difficulties include those types of difficulties which are inherent in the nature of the software, without which the software actually cannot exist. Generally, they are naturally there in the software. So, for example, software is going to use some algorithm, and the difficulty or the complexity or the difficulty of that algorithm is inherent part of the software. The function invocation, the code itself, the relationship among different data sets, all of these are examples of essential difficulties of the software. And inherent properties, as we have already discussed, including complexity, conforming to the requirements, changing and evolving as per the requirements in time, and the invisible nature is inherent in the software. Now, in contrast, the accidental difficulties is a problem in today's production methods. So, for example, you're following a particular process model and there are some few issues and problems with respect to that production or process model. So, those difficulties which are related to the actual production process are generally considered as the accidental difficulties. And of course, this is because they are not inherent in the nature, they are there because of the production process or the software process that we have adopted. Probably if we have adopted something better or something appropriate, we would have avoided this type of problems. So as I have already explained that getting rid of accidental difficulties is possible. So for example, if I have chosen a wrong process model, I'm working with waterfall model, the problems which are there because of that process model can be avoided. They are accidental and they can be avoided by choosing or selecting the appropriate or probably a better process model. So very similar example for this is choosing a low level programming language, or basically the problems or the difficulties in the software development process because of the development language. These difficulties can be avoided by changing the development language. So for example, if I am working in assembly, I can start working in Java. With this, I will be removing an accidental difficulty because the accidental difficulty was brought in by the inadequacy of the assembly language for programming. So in this case, if I have used the object-oriented programming languages like Java instead of assembly, I would have already avoided that difficulty. So we can get rid of accidental difficulties in developing the software. Getting rid of these accidental difficulties will definitely increase the productivity. But when we talk about the essential difficulties, like I have explained in the previous slide, including complexity, conformity, changeability, invisibility, and again this list is not exhaustive, but to overcome this type of difficulties, we have to follow a different approach. But the accidental difficulties can definitely be easily avoided by probably selecting the right programming language, by training your developers, by following a proper UML or any other modeling language, by adopting a correct process model. So you can avoid all the difficulties and problems which may occur during the software development. So here, as this figure states, that the amount or volume of difficulties, whether they are accidental or essential, they are going to increase as you proceed further in the development process. So as far as you go in the development process, you will feel that the amount and volume of these difficulties is increasing. So as we know that complexity is one of the essential property of the software, we know that we can deal with accidental difficulties and accidental properties, but dealing with essential properties is also possible. So as complexity is one of the essential property, or you can consider it as an essential difficulty, managing complexity is the most important technical topic in software development. And of course, there are different ways of doing it. It is so important that software's primary technical imperative has to be managing complexity. So the user should not simply know that what complex set of classes and code or functions are there behind a very simple and good looking user interface. Well, this is the complexity with respect to user, but with respect to development process, the complexity is also very much important. So the goal is to minimize the amount of a program you have to think about at any one time. So of course, whenever we are looking at something very huge and big and large, we can reduce the complexity of that large and huge looking code or class or design by simply dividing it into smaller modules or parts, and then dividing those modules into further smaller sub modules or sub parts. So the average or the ultimate goal is to minimize the amount of program that you have to think about at any one time. And this is the concept of classes, this is the concept of functions, that decomposition is the key for reducing or managing the complexity. So even if we cannot reduce it, we somehow at least can manage it. So we can live with the current level of complexity in a much better and improved manner. Overly costly, ineffective designs arise from three different sources. The very first source or first scenario is where a complex solution has been proposed or given or used for a very simple problem. So probably I just had to take some inputs, process the data and display the results, but I am dividing that into inheritance hierarchies. I'm creating some subclasses and having constructors and some methods and abstract methods, and then I'm actually making my solution complex and complex. So complex solution to a simpler problem, where of course we could have done that in a simple manner. So we should attack the complexity by keeping in view that the problem is simple, the solution should also be simple. We should not have an overhead that we know object-oriented programming is, wow, it's something superficial, or it's something out of this world, and we can use it for any particular problem. But we should see if our problem is simple, and using this particular solution is going to add an overhead, add in a layer of complexity, so we can avoid from that scenario. The second possible state is where a simple or incorrect solution has been given for a complex problem. Now the problem was complex and it really needed a complex solution, or a very detailed or a large solution, but we have attacked it in a wrong way, and we have tried to propose a very simple approach, or basically an inappropriate approach. And thirdly, an inappropriate complex solution has been given for a complex problem. Now we've decided that fine, the problem is complex, a simple solution is not working, so we should work with a complex solution. But that complex solution has to be appropriate. It has to be correct in the right direction and dimension. So these are three different scenarios or sources from where your ineffective designs can basically get a birth. So how should we deal and manage the complexity? There are two possible ways. The first one is to minimize the amount of essential complexity that any one brain has to deal with at any one time, where I told you that you have to divide the code, or divide your design into some subparts, and those subparts into further smaller parts. So minimize the amount of program you have to think about at any one time. You can divide it like divide the code, divide your design into some independent subparts, subsystems, and you should keep your routines or functions short. So for example, if you're writing a function, we are talking about a code, then your function should be a one-page function. So the desirable length of a function is where it can be seen without scrolling your code up or down. Okay, so this is one of the way of dealing or managing the complexity. Another way is to keep the accidental complexity from needlessly increasing. So for example, I should opt for the languages which are simple in nature. I should not go for spiral model because it's itself inherently complex. Okay, so probably I'll be bringing in an accidental complexity just because I have chosen a wrong process model. I'll be bringing in an accidental complexity just because I have chosen a wrong programming language. So you should be very much careful about that the accidental complexities are not being introduced in your development process. There are a few desirable characteristics for a good design. As we are talking about design, as we are talking about complexity, reducing the complexity in our design and in our development process, there are a few different desirable characteristics of a software design. The very first one is, of course, minimal complexity. You should be simple instead of clever. So basically you should see whatever is required instead of going across an extra mile. You should think of the simplest and easiest and the quickest approaches. Ease of maintenance is one of the property for a good design, where I can extend or of course fix or maintain the design basically. Loose coupling. The concept of coupling and cohesion, that's very much related. So you should make sure that your classes are coupled at a very minimal level. So minimal connectedness is desirable. That is why we say that, for example, if I'm writing a class, it must be as generic as possible, so that it should not depend on another class or a number of classes, so that if we have to move that class or change that class, we would be depending on a number of classes. So this should be avoided. Loose coupling means you are minimally connected to other classes, to other components, to other systems. Extensibility, where you can of course extend. So if your code is loosely coupled, it's easy to maintain, it is less complex, then definitely it is extensible. So change a piece of system without affecting the other pieces. Of course, I'll not be affecting the other pieces if I'm not connected to them, if I'm not coupled to them. Then reusability. Of course, again, these characteristics more or less depend on each other. So yes, reusability is another good characteristic, or a characteristic of a good design. Portability, easily move to another environment. So your system should be portable. You should be using a language or a framework or a process model that is portable, that is adoptable. And similarly, use of standard techniques is also one of the characteristics for a good design. Another interesting concept related to design and code is fan in and fan out. So a desirable characteristic is high fan in and low or medium fan out. So when we talk about fan in, high fan in refers to having a high number of classes that uses a given class. So for example, I have a class called printer. Now that printer class should not depend on other classes, rather all the other classes or most number of classes depend on that printer class. So a module that's highly depended upon but itself does not depend on much. So this particular class or this particular module or this particular system does not require other systems or other classes or other modules to work. Rather, it is itself providing the services to other modules, and other people depend upon that particular module or that particular class or a function. So high fan in is the concept where you are not depending on anyone, rather other people depend on you. And in contrast to that, fan out is a number or having a given class use a low number of other classes. So your design, your system, your module does not depend on other number of modules or other classes. So high fan out, more than about 7, indicates that a class uses a large number of other classes and may therefore be overly complex. So for example, if you're using more than 7 classes, so your fan out number is 7, that means you are depending upon 7 different classes. You are actually overly complex. Whereas low fan out is beneficial whether you are considering the number of routines called from within a routine or a number of classes used within a class. So this fan out or fan in technique, it applies to classes, it applies to routines or functions. To basically my understanding, it also applies to a module or to system itself. Whether, for example, if a system is depending upon 7 other systems, that means it is overly complex. Your system should not depend on other systems. Rather, well, in contrast, if other people are depending upon you, then that's fine. You are not overly complex. Other people are using your functionality and you yourself is doing your job. So it says that 7 is a desirable number, or in fact not more than 7 or less than 7 is fine. Another characteristic is leanness, where designing the system so that it has no extra parts. It is simple, it is self-composed, it is not having any extra code or extra classes or extra methods, is defined or is said to be lean. So extra code has to be developed, it has to be reviewed, it has to be tested and considered when other code is modified. So you should make sure that you are doing what you are supposed to do, and that's it. You're going in a very straight line. Okay, so this is going to help you to provide or to generate a code which needs less reviewing, less testing, and of course you will have less errors. One very common example of non-leaned code or non-leanness is where the Ariane 5 actually exploded after its flight in the air. Well, before I continue, let's have a look at the Ariane 5 explosion video.
Attention pour décompte final.
A final decision to go was taken.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage. Décollage. paramètres propulsifs sont normaux et la trajectoire est normale.
37 seconds into the launch, the onboard computers decided 501 was 90 degrees off course. They made an automatic adjustment to the trajectory as the rocket was traveling at the speed of sound.
So this proves that extra code is always a problem, and it would definitely result into something that you actually do not want. Now, the last part of today's discussion is different levels of design, which of course I'm going to go through very quickly because we are already familiar with what software design is. We have already gone through software design and architecture. So design is needed at several different levels of detail in a software system. We can have a lower level design, a higher level design, a medium level design, and so on. Some design techniques apply at all levels and some apply at only one or two. So there are certain levels of a design, including software system, division into subsystems or packages, then dividing those subsystems or packages into classes, dividing your classes into data and routines, and then of course designing your internal routine. So that's the level of design that you do basically, where this is the higher level design. Probably as you move forward, you are moving to the very lower level. So we can have a software system where we have a complete system. We divide that system into some subsystems or packages. Then we further try to design or divide those subsystems and packages into classes, and we design this. We design that, and later on we try to design or divide our classes into different data parts and function or methods, and lately we design the individual methods, which are technically called routines as well. So in the software system or the level 1, we design the entire system. In level 2, we identify major subsystems, database, user interface, business rules, and all that. And some common subsystems may include business rules, UI, data access, system dependencies, some other external libraries which you are using could be part of your level 2 design. So this is again an example of level 2 design. And in level 3, you divide your subsystems into classes, where your class interfaces are defined, your class inheritance hierarchies are defined. And in level 4, we divide our classes into routines, whereas at level 5, we perform the internal routine design, laying out the detailed functionality of individual routines. So this is the overall hierarchy and view of the levels of design and characteristics of design, and we also discussed what are essential and accidental difficulties in software design and software development process. So with this, we will stop here, and we have somehow concluded the design in construction. What specific aspects do we need to take care of while we are thinking to start software construction, as design is overlapped, as design is again one of a part of software construction, so we should be very much careful about that. With this, I will stop here and see you in the next lecture, and thank you.